The hidden science of catastrophic failure. A rocket that was supposed to fly east suddenly turned north, flew completely stable for 4 full minutes, and had to be killed by a safety officer 484 seconds after launch. That sentence comes from page 143 of a United States Department of Defense technical report. Not classified, but buried so deep in bureaucratic language that almost nobody outside a small circle of Air Force safety engineers ever read it. The report was produced by the Research Triangle Institute under contract number FO4703-91-C-0112, finalized September 10, 1996. And what it describes is something that the people responsible for launching rockets into the sky had quietly understood for decades. That under the right, or rather the wrong conditions, a failing rocket doesn't just blow up. It can turn around, it can fly towards cities, it can go anywhere. But the truly chilling detail isn't in that sentence. It's in a calculation buried near the end of the document, a number that the Air Force used to determine how likely it was for a rocket to deviate catastrophically towards populated areas. That number had been set to a particular value for years, and when the authors of this report sat down to actually test whether it was right, what they found changed the math entirely. We'll get there. First, we need to understand why this report exists at all. The document is officially titled Modeling Unlikely Space Boosters in Risk Calculations. That title is bureaucratically neutral to the point of being misleading. What the report is actually about is building a mathematical model for what happens when a rocket decides to go where no one intended. The engineers who wrote this, James A. Ward Jr. and Robert M. Montgomery of the Research Triangle Institute, were tasked with a specific problem. When the Air Force launches a missile or a space vehicle from Cape Canaveral or Vandenberg Air Force Base, there is always a safety officer watching. That officer has one job. If the rocket goes wrong, press the button that destroys it before it can hit anything. But the safety officer needs time, a few seconds to evaluate data, a few seconds to make a decision. And in those few seconds, a malfunctioning rocket with its engines still firing can move the impact point, the location on the ground where it would fall, a remarkable distance from the intended flight line. The software program they used for risk analysis was called DAMP, Facility Damage and Personnel Injury, and DAMP needed a special model for the most dangerous kind of rocket failure, the one they called Mode 5. Here's what makes Mode 5 different from everything else and why it matters so much. When most rockets fail, they fail in predictable ways. The engine cuts out, the vehicle tumbles, and debris falls more or less where you'd expect, near the launch pad or somewhere along the intended flight path. These are modes 1 through 4, messy and dangerous, but geographically bounded. Mode 5 is the failure that doesn't respect geography. In a Mode 5 event, the report says, a rocket may impact in any direction from the launch point within its range capability. Any direction, uprange, cross-range, towards cities that have nothing to do with the intended trajectory. And the report is very clear that this is not theoretical. They give you examples, real flights, real vehicles, real people watching from safety consoles as rockets did things no one planned. Hold on here because these examples get stranger the more closely you read them. On September 18, 1968, a Delta rocket carrying the Intelsat 3A communication satellite lost a rate gyro 20 seconds into flight. What followed was something the safety records describe with clinical precision. The vehicle pitched down 270 degrees, then up 210 degrees, then made a large yaw to the left. For 13 seconds, the rocket executed violent maneuvers while its engines were still firing. Then, somehow, it regained control. It flew stably in completely the wrong direction until 100 seconds when aerodynamic forces overwhelmed it. Major pieces impacted 12 miles downrange and 2 miles left of the flight line. 12 miles from the pad, 2 miles sideways, with a rocket that had effectively been flying drunk for nearly 2 minutes. Then there was Pioneer E, August 27, 1969. The first stage hydraulics failed near burnout. The vehicle pitched down, yawed left, rolled counterclockwise, and drove all gyros off their limits. The first stage tumbled completely out of control. But then the second stage separated and ignited on its own anyway, while the vehicle was still spinning. And what happened next is what earns this case its place in the Mode 5 category. After about 20 seconds, the second stage regained control on its own. It stabilized itself in a nose-up, yaw-right attitude, completely different from anything planned. And then it flew, stably, for 4 minutes, until the safety officer finally destroyed it 484 seconds after launch. This is actually written in an official government document. A rocket that should have died instead composed itself, oriented itself, and flew for almost 8 full minutes in the wrong direction because no one was willing to press the button when it wasn't technically threatening the impact limit lines. It looks like a normal report, but when you read between the lines, you start to understand what the authors are actually documenting. A history of the government knowing that rockets can go rogue, survive, and continue thrusting in arbitrary directions, and trying to build a mathematical function that captures how likely they are to hit you if you happen to be in the wrong place. That function is at the center of this document. It has two shaping constants, A and B. And for years before this report was written, the Air Force had been using A equals 3.0 and B equals 1,000 for their risk calculations. Those weren't numbers derived from careful analysis of actual Mode 5 events. There weren't enough Mode 5 events to derive anything statistically. They were, in the author's own words, values chosen based on earlier intuition and adjusted slightly over time as vehicles seemed to deviate less. But here's what the report reveals. No one had ever properly tested those constants against what actually happens during a controlled simulation of a Mode 5 malfunction. So Ward and Montgomery built a computer program. They called it RAFIP, Random Attitude Failure Impact Point, in Fortran. 3,900 lines of code, running on a personal computer. And using this program, they ran simulations. Not dozens, not hundreds, hundreds of thousands. For the Atlas II-AA rocket alone, they ran 1,080,000 simulated failure trajectories. At each of 28 different failure times, 10,000 simulated rockets went wrong, oriented themselves randomly, and the program calculated where they would land. Then they compared those impact distributions to what the old Mode 5 density function predicted. What I'm about to show you explains why the Air Force commissioned this study in the first place, and why the results forced them to reconsider the numbers they had been using. The shaping constant A, it turned out, was not simply 3.0 for all vehicles and all conditions. It depended critically on something the old calculations had largely ignored: how strong the rocket was. Specifically, whether it could survive the aerodynamic forces of flying sideways through the lower atmosphere without breaking apart. The weaker the rocket, the lower the dynamic pressure needed to tear it apart, the more quickly it would disintegrate during a malfunction turn, and the less far it could deviate from the flight line. A vehicle that broke apart quickly had an effective A value of around 3.45. A vehicle that was built ruggedly enough to survive long sideways flight, the no breakup case, had an effective A value as low as 1.9. That is a massive difference in terms of the risk contours damp would produce for population centers uprange from the launch pad. Can you believe this? The entire mathematical basis for calculating how likely a rogue rocket is to hit a populated area depended on a structural assumption: how tough the rocket's skin was, that had never been systematically tested before 1996. At this point, we can no longer call it a coincidence that the report also contains a complete failure history of every Atlas, Delta, and Titan rocket launched from American ranges since the beginning of each program. Appendix D is 75 pages. It lists every flight, every failure, the response mode, the flight phase, the brief narrative of what went wrong. Reading it is like reading the minutes of disasters. January 24, 1961, Atlas 8E. The rocket that lost stability 30 seconds after main booster cutoff flew for another 87 seconds with its sustainer engine firing and impacted 1,316 miles downrange and 215 miles cross-range, with a rocket that kept thrusting for a minute and a half after control was lost. Or December 8, 1980, Atlas 68E. The rocket that lost a booster engine had the asymmetric thrust spin it into retrofire attitude, pointing backward, stabilized while pointing in the wrong direction, and kept thrusting that way until re-entry heating shut down the engine at 282.9 seconds. These are not near misses in any comfortable sense. They are demonstrations that the range of possible impact points for a malfunctioning rocket is genuinely global in character, limited only by the vehicle's remaining energy. But here is what the report ultimately concludes, and why the baseline risks it computed matter so much for anyone who has ever lived within a few hundred miles of a launch rocket site. When Ward and Montgomery recomputed the Mode 5 baseline risks for Atlas and Delta using their new methodology, the new failure probabilities, the new shaping constants, the new understanding of what actually happens during a Mode 5 malfunction, the risks in the launch area went down significantly. For Atlas, the reduction factor was between 3 and 11 times lower than previous estimates, depending on how robust you assumed the vehicle to be. For Delta, the reduction was between 4 and 75 times lower. That sounds reassuring. The new math said rockets were less dangerous than previously thought. Except, the report also notes, quietly, in the section on future investigations, that the Mode 5 shaping constants they derived are based only on two types of simulated malfunctions: random attitude failures and slow turns. The authors acknowledge explicitly that many other types of
Mode 5 responses exist that are, in their words, so convoluted that they defy description or categorization. The math is better than what came before, but it is still incomplete. There are still failure modes that no one has found a way to simulate. And then there is this. The exponential filters used to estimate future failure probabilities for Atlas, Delta, and Titan were designed to give more weight to recent launches and less to old ones. The most recent Atlas data point, from January 31, 1996, was weighted 22.9 times more heavily than a launch from 1964. That sounds reasonable, but it means the filtered failure probability for a vehicle that has been reliable recently could mask the existence of rare failures, the 1 in 100 or 1 in 200 events that have simply not yet appeared in the modern dataset. The report says this directly. If some characteristic exists in exactly 1% of a population, there is a 37% probability it will not appear at all in a random sample of 100. The failure has been invisible, but it has not been eliminated. After all these pages, 172 of them, dense with equations, flight histories, impact density functions, shaping constants, and filtering methodology, only one question remains. If you are standing uprange from a rocket launch, how confident should you be in the number that says your risk is acceptable? The answer, according to this document, is that it is the best available estimate, derived from hundreds of thousands of computer simulations, filtered from decades of actual flight history, calibrated against actual vehicle structural properties. It is rigorous, it is careful, it is the product of serious engineering effort. But the authors themselves wrote in the section on potential future investigations that several significant factors could not be fully examined due to contract limitations on funds and the deadline for publishing the report. They ran out of money before they finished. The math was improved, the gaps were documented, and the rockets kept flying.